We're going to now look at the questions in exercise 12.4. So we got this information given at the top. So in the following questions where necessary, take G, the universal gravitational constant, to be 6.7 by 10 to minus 11 newtons meters squared per kilogram squared. The radius of the Earth is 6.4 by 10 to the 6 meters. So again, that's the distance from the center of the Earth to a point on the surface of the Earth. You might need this if you're on the surface, or you might need to add a distance if you're up in the sky. Then you have the mass of the Earth is 6 by 10 to the 24 kilograms, so that's our standard information for all of these questions. So it tells us a satellite orbits the Earth in a circular orbit at a height of 50,000 kilometers. With what speed does it travel? How long does it take to make one revolution of the Earth? So again, these are the kind of things we can now deal with. So it tells us the height of the Earth is 50,000 kilometers, which is 50 million meters. And that's the only information we're given, and thankfully that's the only information we need. So if we look at this, we have the radius of the Earth plus the height. So that's why doing a diagram is useful, because you could have just taken that figure. You also need to add in the radius of the Earth, the 6.4 by 10 to the 6. So our formula here is the velocity is the square root of gm over r. So v squared equals gm over r, and then we take the square root of both sides to find out what v is, because we want that not v squared. So our radius is the radius of the Earth plus the height, which is 6.4 by 10 to the 6 plus 50 million, which gives me this figure here, 5.64 by 10 to the 7 meters. We sub in the figures there. G is the universal gravitational constant, m is the mass, and r is your radius, your total distance, which is this. Throw them into your calculator and you get this as your answer. So that's a ferociously big speed, 2,669.8 meters every single second. So that is our answer to that. Next, the time for one revolution. So this is asking us for the period t, and again it's tricky to get used to some of these letters, but the period is t. Formula for period is 2 pi r over v. Now again, we have all of this information now, so it's relatively straightforward. T is 2 pi by r, which is the radius, which we calculated above, over v, which is our speed. So then we do that calculation, we get this number of seconds, which could be an okay answer. What is it? 132,733.41 seconds. So we can then convert that into hours. So it's 36.87 hours. You divide it by 60 to get minutes, and divide it by 60 to get hours. And then I converted it into hours, minutes, and seconds. But even that took a bit of rounding off. So this answer here would be okay, 36.87 hours. So that would be more than a day for it to do its period. So question 2, a satellite orbiting the Earth in a circular orbit takes 30 minutes to go around once. What is the radius of the orbit, and with what speed does the satellite travel? So again, we're told it goes around in 30 minutes. So 30 minutes is 1,800 seconds, and we're asked to find the radius of its travel, so how far it is away from the center of the Earth. Because we have the period, we'll use this formula, t squared is equal to 4 pi squared r cubed over gm. And again, all of these figures here are going to be constant. 4 is 4, pi is pi, g is a universal constant, and m in this case is fixed as the mass of the Earth. So t squared is equal to 4 pi squared over gm times r cubed. So I just wrote that a bit separately. I put all of the constants together here. So then I cross multiply, so multiply both sides by gm, so I get gm t squared equals 4 pi squared by r cubed. Then I divide both sides by 4 pi squared, so I get this here. Then I get the cubed root, and I much prefer doing the algebra before you do the substitution, because it's much easier to write the letter g than this big long symbol here with the unit. Similarly, pi, even 3.14 is an approximation. You don't want to be writing these things out over and over. So I would recommend doing your algebra and then doing your substitution all at once. So we get here the radius is 3.2 by 10 to the 6 meters. That's what we asked for. So it's that far away from the center of the Earth. Then to get the velocity, we use the same formula we used before. V squared is equal to gm over r. Get the square root of both sides to give you this. So in your figures, we know g, we know m, and we've just found the radius, so we can then quite easily get the velocity of 11,208 meters per second. So again, a very, very big speed. On to question 3. We have the planet Jupiter orbits the Sun in an orbit of radius this. So they're giving us the distance, the radius of the orbit. Given that the mass of the Sun is 2.0 by 10 to the 30 kilograms, calculate the time taken for Jupiter to complete one orbit of the Sun. So again, what that basically means is what is a year on Jupiter. A year is the time taken to orbit the Sun once. So what is that for Jupiter? We have the radius, we have the mass, so we need to find the time taken. Radius is this, the mass of the Sun is 2.0 by 10 to the 30, and we're asked to find the time taken for one orbit, which is known as the period. So we're looking for this t squared, 4 is 4, pi is pi, r cubed, we're given the r so we can do that, g we know and m we know, so this is just a case of subbing them all into the formula. We want t, not t squared, so we get the square root of both sides, which gives us this. We sub in our figures, and we get an answer of 11.9 years. Now again, that will be 11.9 Earth years, and it will be 1 year for Jupiter. So again, you have to standardize these things. So when I say 11.9 years, I'm talking about Earth years. Question 4 tells us the radius of orbit of the planet Saturn is 9.5 times the radius of the Earth's orbit. Find the time taken for Saturn to make one complete orbit of the Sun. Again, anytime you get these ratio questions, so 9.5 times something else, that is a clue that A, it's going to be a bit more difficult, and B, that you're going to need to let one thing equal the other, or write one thing in terms of the other. So in this question, we stick with ratios, and it makes life a little bit complicated, but I'll talk you through it as best I can. So all we're told in the question is the radius of Saturn, so RS, is equal to 9.5 times the radius of Earth. So that's 9.5 times RE. So that's the only information I have. We're asked to get the time taken for it to complete one orbit, so that gives us a clue that we're looking for the period of each of those. So the period for Earth, so TE, that is equal to this, and the mass that we're looking at is the mass of the Sun, because that's the mass of the central body. The mass of the satellite, in this case the Earth, because that's the thing that's going around, that doesn't matter. So it's the mass of the Sun is equal to this, and then we do the same thing for the period of Saturn. So the period of Saturn written here in blue, the period of Saturn is equal to this. So we have these two separate formulas. And because we have this relationship here, that's our clue for what we do next. So we have limited information here, so all I can work with is this ratio. We do have a lot of common terms. Again, you can see most of the equations are the same, so this will help us to find the relationship. So because I know one is 9.5 times the other, I can do this bit of division here. So I write 1 divided by the other, and I'll be able to get my answer from here, and this is a common trick that you'll use in these sections. So the period of Saturn divided by the period of Earth, that is equal to this, and there's no problem in doing that because we divide this is equal to this is equal to this, so we can divide one by the other and it's going to stay equal. It's like if any equation you divide both sides, it's all the same thing. So because we have all of these similar terms, we can cancel 4 pi squared, we can cancel g with g, we can cancel the mass of the Sun with the mass of the Sun, so it reduces down to this formula here. You wouldn't need to do this every time, but I think it's good to see where it comes from. This is the relationship that you would get, and this is the relationship it has to be, because all of those terms will always be in common. Again, what I did in the bottom here, I inverted and multiplied, so that's what you do to divide by any fraction, invert and multiply, and that makes the cancelling a bit more obvious. So 4 pi squared with 4 pi squared, g with g, mass of the Sun with the mass of the Sun, so we get the radius of Saturn cubed over the radius of Earth cubed, and that's our relationship here. Now we can do a little bit more algebra with this. This is ts squared over te squared, so we can just take that whole thing squared, and this is rs cubed over re cubed, so we can take both sides cubed. We know this from the question, rs is equal to 9.5 times re, so we can then get down to this relationship here. So ts over te squared, rs, I can write that as 9.5 times re, so again 9.5 re over re, so they cancel, so that makes my life a good bit easier, and I'm almost at my solution here. And again, this is kind of working from step 1. Anytime you get a question like this, you can kind of jump straight in here because it's going to be the same thing all the time, so you can make your life a little bit easier, but I do like to show where it comes from. So we have this relationship here, and then I carry this through, so I get 9.5 inside the bracket, I get the square root of both sides, I multiply both sides then by TE, I'm cross multiplying as I think in my head. So TS is equal to TE times this here, the square root of 9.5 cubed. So TS is equal to this. So it's 29.28, that's what that calculates to, times TE. What is TE? Well, that's the period of one Earth year, so that's my 365.25 days, or however you accurately want to do it. So the period of the Saturn is 29.28 times the period of Earth. As the period of Earth is 1 year, the period of Saturn is 29.28 Earth years. I should probably have written Earth years in here. So that's how long it takes. It's nearly 30 times an Earth year, so it's nearly 30 years, as we would call it. And again, the algebra you do for this question for any planet, all that would really change is you're going to end up with, well, if you really want a shortcut, you're going to end up with this thing here. So because it was 9.5 Earth years, you end up with this relationship here. If it happened to be 6 times the radius of Earth, you'd end up with a 6 in here. If it was 17 in it, 17 in here. So you really can't shortcut these questions because the algebra will always be the same because it's the same context and the same numbers, and no matter what the numbers were, even they're going to cancel. So you really could shortcut down to that thing there. On to our next question, question 5. One of the moons of Saturn is in orbit which has approximately the same radius as that of Earth's moon. Given that the speed of the Saturn moon is 10 times the speed of the Earth's moon, calculate a value for the mass of Saturn. So again, pick out your information. The mass of Earth, we're told earlier, is 6 by 10 to the 24 kilograms. The velocity of Saturn's moon is 10 times the velocity of Earth's moon. So that's what my subscript down here is. Velocity of Saturn's moon is equal to 10 times the velocity of Earth's moon. And we know that the radius of Earth is roughly equal to the radius of Saturn when we talk about these. So one of the moons of Saturn is in orbit which is approximately the same radius as that of Earth's moon. So we have these two things here being equal. So Earth moon, radius of Saturn moon. So I could have gone with that a little bit more. So here's my general formula. B squared is equal to gm over r. That will be in my tables. So then I can apply this to both situations. So the velocity of Saturn moon squared, that's equal to g by the mass of Saturn over rs. Again, it's important to know where these come from. So I'm looking at the velocity of Saturn's moon. That's the universal gravitational constant by the mass of Saturn. So again, that's the key. That has to be the mass of Saturn because it's going around Saturn. And it's the radius of Saturn. So again, the distance from Saturn to the moon, the center to center, that will be my rs. Equally for the velocity of Earth's moon, it's going around the Earth, so we take me, and it's the distance from the center of the Earth to the moon. So it's, I had Earth moon there, but it's not. It should be the radius of the Earth and the radius, the distance from the planet to the Earth. That's the key thing there. Now, because it's another ratio question, we're going to divide just like we did before. So we divide the velocity of Saturn's moon by the velocity of the Earth's moon, and the right hand side by the right hand side. Those things are equal, these things are equal, so we divide by the same thing. That's all well and good. Like before, to make my life a bit easier to show it, I'm dividing here, so I invert and multiply. I can cancel g and g, and I end up with this relationship here. So again, as before, we have both of these things squared, so we can square the whole fraction. We then have radius of the Earth over radius of Saturn, so I put the two radiuses together, and I have the mass of the Saturn moon, or the mass of Saturn, mass of Saturn over the mass of Earth. We know from a question that the radius of Earth is approximately equal to the radius of the Earth moon is approximately equal to the radius of the Saturn moon, so they will give us 1. They're about the same thing, so they'll cancel out, divide to give us 1. And we also know that the velocity of the Saturn moon is equal to 10 times the velocity of the Earth moon. So this thing over here, we can substitute, so the velocity of the Saturn moon is 10 times the velocity of the Earth moon. So when we substitute those things in, so that divides to give us 1, so we end up with the mass of Saturn over the mass of Earth. We have the velocity of Earth moon over the velocity of Earth moon, they cancel to give us 10. So this then tells us that 10 squared is equal to ms over me. I square 10 to get 100, and I multiply both sides by me, so it's 100 by the mass of Earth is equal to the mass of Saturn. So then I know from earlier that the mass of Earth is 6 by 10 to the 24 kilograms, so I can substitute that in. So it's 100 times heavier than Earth. Earth is this, so it's 6 by 10 to the 24 times 100, which gives me 6 by 10 to the 26. So that's a way to show that the mass of Saturn is 100 times the mass of Earth. So that's again all you need to know. Again, there's a good bit going on in that question, but no matter what information they give you, there's not much they can do with it. Physicists will always give you accurate figures, so the mass of the Earth will always be that figure. And again, if you look kind of how the algebra works, because the velocity of Saturn's moon was 10 times the velocity of the Earth moon, you're going to get down to this kind of thing here. So whatever number they give you, square it equals the mass of the planet you're looking at over the mass of Earth. Then you get this line here. So you could kind of shortcut a lot of this stuff and there wouldn't really be a huge problem. More to remember. So if you work it from first principles, you got more work to do. If you try to remember this, you got more to remember, but they will always give you the same formulas, the same relationship. On to question 6. It says find the radius of orbit and speed of a satellite stationary above the equator. So again, this is a typical question. So the period is 1 day, which is 24 hours. So because it's going around the Earth, it's 1 day, and that multiplied by 60 gives you 86,400 seconds. Mass of the Earth is 6 by 10 to the 24 kilograms, and period in general is this formula here. So if we rearrange this, because we're trying to find the radius of orbit, we're trying to find the distance from the satellite to the center of the Earth. So we're trying to calculate what r is. So again, it's going to be t squared by gm. That's giving my top line. I will then divide across by 4 pi squared, and I'll get the cubed root of each side. So that's what my radius is. I think I just copied that from the textbook or from the notes, but it is just a bit of algebra to do that. Do your algebra before you substitute, but when you substitute, you're going to get a big long line of figures like this. So that is my period. That is the universal gravitational constant. That is the mass, and that is 4 pi squared. And again, keep your units so you know what's what. Then you throw this into your calculator and you get the answer that this is 4.24 by 10 to the 7 meters from the center of the Earth. And again, that's a figure worth remembering because any satellite that's stationary above the equator has to be this distance from the center of the Earth. If you are asked the height, then you got to do that bit of subtraction. Then you find the speed of it, which is again going to be a constant figure. You could just remember it. So the velocity squared equals gm over r. That's our general formula. Get the square root of both sides. Sub in your figures. G, universal gravitational constant. M, the mass of the Earth. Or the radius that we just calculated. And we get this figure then for your speed. So it's 3,079 meters every second. Then we get on to question 7. The radius of the Earth at the equator is this, which is again accurate figure. So find first off the linear speed of a particle at the equator. So if you were sitting in a chair at the equator, how quickly would you be going? That would be your linear speed. If the Earth stopped, for example, you would be sent flying forward with a particular speed. And then secondly, the acceleration of a particle on the Earth's equator. Now we know this is non-zero because an object in circular motion is said to be accelerating, which gives it a force and so on. So again, we have our information. The radius of the Earth is this. So as this is circular motion, 1 revolution is the angle you're going to move through. You're going to go around in a full circle, so that gives you 2 pi radians. The time it takes is the period, which is 1 day, which is 86,400 seconds. The radius we're given, so we take that there. Now again, remembering back to our previous formula, your angular velocity is the angle traveled over the time taken. So this is 2 pi because you go around a full circle over 1 day, which gives you this as your answer. So it's 7.27 by 10 to the minus 5 radians per second, which is really, really small. You've got to move your decimal point 4 places there, so it's 0.0000727 radians every second. So you're tracing out only a tiny angle every second. Then that was the first bit. So we then need to get the linear speed. So this is kind of like a preliminary step. Your speed, again from previous sections, is omega r, the angle you trace out by the radius, because the further you go away, the quicker you travel. So if this tiny angle multiplied by a huge radius, because the radius of the Earth, so you sitting still at the equator will be traveling at a speed of 465 meters every second, which is a very, very big number. It's faster than the speed of sound, in fact, which is about 300 meters per second. Then you get your acceleration. So your acceleration again is omega squared, or omega we found up here in blue, so that is that squared. Remember to square it by the radius, which gives you this very small figure here. So it's 0.0338. 5 if you're super accurate, but if you do any rounding, it'll round down to this. So your acceleration is this figure here. So your angular speed is very small, your acceleration is very small, but you are traveling at a huge speed. It doesn't feel like it, but that's what the physics shows you. Then that's the end of our section. So best of luck understanding those.